In this video, we're going to discuss the types of diffusion models and how they work. So let's begin. Diffusion models are generative models that have revolutionized the world of artificial intelligence. These models are designed to generate data by simulating a process of gradually adding noise to the data and then learning to reverse this process. Imagine starting with a clear image, adding random noise until it is completely distorted, and then training a model to recover the original image from this noisy version. This forward and reverse process is the essence of diffusion models, allowing them to generate high-quality, realistic data. Now let's delve into the different types of diffusion models and how they work. One of the most prominent types is the Denoising Diffusion Probabilistic Model, or DDPM. These models work by breaking down the generation process into a series of small, incremental steps. In the forward process, an image is progressively corrupted step by adding noise in small increments. The reverse process starts with a noisy image and gradually removes the noise to recover the original image. This step-by-step denoising is guided by probabilistic distributions learned from the data, ensuring that the model can produce high-quality outputs. Think of DDPMs as meticulously sculpting a masterpiece from a block of marble, where each step brings out more detail and structure. Another intriguing type of diffusion model is the noise-conditioned score-based generative model. These models take a slightly different approach compared to DDPMs. Instead of directly modeling the denoising process, they learn to estimate the gradient, or score, of the data distribution. This score represents the direction in which the model should move to increase the likelihood of generating realistic data. During training, the model is exposed to data with various levels of added noise learning to predict the gradient for each noise level. During generation, this learned gradient guides the transformation of noise into realistic data. The process resembles that of a painter using an outline sketch to create a detailed painting. The sketch guides the brushstrokes of the painter, ensuring that the final artwork is coherent and follows the desired form. Lastly, we have the stochastic differential equations, or SDEs, in diffusion models. SDEs provide a powerful mathematical framework for describing systems that evolve over time with an element of randomness. In the context of diffusion models, SDEs are used to formalize the process of adding and removing noise continuously over time. This continuous time perspective allows for more sophisticated and flexible modeling compared to discrete steps. SDEs describe how noise is added to the data in the forward process and removed in the reverse process, enabling the use of advanced mathematical tools for efficient and accurate generation. Imagine SDEs as the movements of leaves in a gentle breeze. The path of each leaf is influenced by both the steady direction of the wind and random gusts, creating a smooth yet unpredictable motion. Together, these models form a powerful toolkit enabling the creation of realistic synthetic data that drives innovation across a wide range of fields, from image synthesis to scientific simulations. By mastering these models, we open the door to new possibilities in generative AI and beyond.